Avery, the application astronaut, talking to you about optimization. Now I got a question. How do you get a baby astronaut to sleep? You rocket.
First thing we're going to talk about is optimization. That would be the determination of the minimum or maximum values such as greatest profit, least cost, least time, greatest voltage, optimum size, least size, greatest strength, greatest distance, etc. So in this section, you're going to be given some real-world scenarios in which you're going to need to either minimize or maximize certain values like profit or cost or time. Now we know how to do this. All we need is the equation that corresponds to the profit, cost, time, or voltage, etc. So if we have that equation, then all we have to do is find the critical numbers, and then we can figure out what our relative max and min values are and answer the question. The equation we're going to use to find the maximum or minimum values is called the primary equation. That's the equation that gives the formula for the quantity to be optimized. So this little blue line here represents our primary equation that we're going to need to find the critical numbers of in order to optimize our given real-world scenario. Now let's talk about how to solve applied minimum and maximum problems, or optimization problems. First thing you're going to do, very similar to related rates, we're going to make a sketch. We're going to label all constant measures with a number and give a variable to all measures we're optimizing. Then we're going to state the given quantities and quantities to be determined. So in your sketch, you may see that some measurement has to be fixed. It has to be a certain measurement no matter what. That is the only thing you can label with a number. Any measurement that is part of the optimization process must be given a variable. Then, just like normal, we're going to state what we're given and what we're trying to figure out. Then, in step 2, we need to write our primary equation for the quantity that is to be maximized or minimized. So whatever you're maximizing, you need to write an equation that involves that thing. Typically, these equations are going to be volume formulas. They're going to be surface area formulas. They're going to be distance formulas, something like that. Then, in step 3, we're going to reduce the primary equation to having a single independent variable. This may involve the use of secondary equations related to the independent variables of the primary equation. So we did this in related rates too. Your primary equation, let's say it's a volume formula. It may have more than one independent variable. In order to move on to the next step though, we need to make it so it only has one independent variable. So you're going to need to go back to the original question, look at your given quantities, and use one of those given quantities to write one independent variable in terms of the other. So then you can plug it back in to the equation and you only have one independent variable. We can only have one independent variable because in the next step, we're going to find the critical numbers of our primary equation, which means we're going to take the derivative of our primary equation, set it equal to 0, and solve for x. From there, we can then determine which are our maximum and minimum values. After that, the very last thing you're going to do, after you have your answers, you're going to ask yourself, does my answer or do my answers make sense? I.e., are there no zero or negative measurements where there shouldn't be? Is one of the side lengths of my box negative? Is the height of my cylinder 0? If that's the case, then those cannot be answers to the question because those measurements don't make sense in real world scenarios. The last note here is just that no two problems are the same. It's very much like related rates. These are word problems. They're all going to be a little bit different, but you still follow these 5 steps.
Why do astronauts wear bulletproof vests? To protect against shooting stars. It's example time.
Now example 1 says a manufacturer wants to design an open box having a square base and a surface area of 108 square inches as shown. What dimensions will produce a box with maximum volume? So let's go through our steps for optimization problems. The first one is we are going to make a sketch. Oh, they already give it to us. And then we're going to label any constant measures with a number and any measurements that we're trying to optimize with a variable. Oh, they already do that for us as well. Awesome. After that, we have to state the given quantities and the quantities to be determined. So let's start with our given quantities. What are we given here? Well, it looks like we're given that this open box having a square base has a surface area of 108 square inches. Now, what are we trying to figure out? Well, we are trying to figure out what dimensions will produce a box with maximum volume. So the length, width, and height of our open top box. Step 2 is to determine our primary equation. So what are we trying to maximize or minimize in this case? Well, Well, it says we're trying to find the dimensions that will produce a box with a maximum volume. So we need the volume formula for a box. A box is another word for a rectangular prism. So the volume formula for a rectangular prism is just length times width times height. In this particular instance, it is an open box with a square base. Now the open box only really factors into the surface area because it doesn't have a top. But the volume of the box remains the same even without a top. Also, the important part for the volume formula is that it has a square base, meaning that the length and the width are the same measurement. That's why here they label them both with an X. So over here, we're going to rewrite the volume formula instead of length times width times height. We're going to rewrite it as X times H, or X squared times H. Now in step 3, we need to make sure that our primary equation only has one independent variable because we have to take the derivative of it later. So if our volume formula is X squared times H, we need to figure out how do we write X in terms of H or H in terms of X. Well, again, you need to go back to your given quantities. What are we given? We're given the surface area of this open top box is equal to 108 inches squared. Now we're going to use this to make sure that we only have one independent variable. How do we do this? Well, the surface area of this open top box is equal to the area of the base plus the area of all the sides added together. So what is the area of our base here? Well, that's X times X, so that's X squared. What's the area of a side? That would be X times H. And how many sides are there? There's 1, 2, 3, 4. So the surface area for this particular figure over here would be X squared plus 4 times X times H. Now, how does this help us? Well, we can now solve this surface area formula for one of our variables up here. And then we can take whatever it's equal to, plug it in up here, and we would only have one independent variable. So what I'm going to do is I'm going to solve this for H. I'm going to subtract X squared on both sides. I'm going to divide both sides by 4x, and I get H is equal to 108 minus X squared over 4x. Now what I can do, I can take this value that H is equal to, and I can plug it in for H in our volume formula, making it so we only have one independent variable now. Now I can simplify this a little bit more by distributing the X squared to the 108 and the negative X squared in the numerator, then putting 4x under each term in the denominator and simplifying, and I end up getting my volume formula with only one independent variable. Now we can move on to the next step, which is to find our critical numbers so that we can determine our maximum or minimum values. Again, to determine the critical numbers, we need to find the derivative of our primary equation. Now when we take the derivative here, we take the derivative of 27x. The 27 just stays out front, and then you take the derivative of x, that just becomes 1. So 1 times 27 is just 27. Over here, the derivative of negative x cubed over 4. We can take the negative 1/4 and move it out front of the derivative sign, and then just take the derivative of x cubed using the power rule, so it becomes 3x to the second power. Then the 3 multiplies to the negative 1/4, and you get something that looks like this. So we've taken the derivative of our primary equation, but to find the critical numbers, we need to set that equal to 0 and solve for x. So here, how do we solve this for x? Well, we add 3x squared over 4 to both sides, multiply both sides by 4, divide both sides by 3, and then square root both sides. We get x is equal to positive or negative plus or minus 6. Now we look up here, our open top box, the x would be the length and the width of that box. Well, it can't be negative, right? Because we can't have a negative side length of our box, which means x has to equal 6 inches. Now, we have found the length and the width of the box, but we still need to figure out what the height is because we need all of the dimensions. So how do we figure out the height? Well, didn't we earlier figure out what the height was equal to in terms of x? Yeah, we plugged it in here. The height was equal to 108 minus x squared over 4x. So we can take that equation and find the height by taking 6 and plugging it in for x. If we do that and simplify, we end up getting that the height has to equal 3 inches. So to answer this question, because it's a word problem, just like related rates, we need to answer in a sentence. A box with a surface area of 108 square inches would have a maximum volume if made 6 inches by 6 inches by 3 inches. Now, example 2 says the owner of DeLazzer's Donuts wants to save money on his open top boxes. If the boxes must have a square base and a volume of 1,000 cubic inches, what dimensions would minimize the amount of material to be used? So notice how it says minimize the amount of material to be used. Anytime it says minimize or maximize something, you need to realize that it's an optimization problem. So we need to go through our steps. The first step is to make a sketch. Boom, they already did it for us. Nice. In that sketch, we need to label any constant measures with a number. number, and anything that we're maximizing or minimizing needs to have a variable. Well, clearly, we are minimizing the amount of material to be used, which involves the dimensions of the box. So the dimensions, the length, the width, and the height, should have variables, which they do. So we can move on to the next part, which is to state our given quantities. What are we given? We're given that it's an open top box, meaning that it's missing the top, and we're given that the volume of this open top box has to be 1,000 cubic inches. Next, we need to figure out, what are we trying to find? Well, we're trying to figure out what dimensions would minimize the amount of material to be used. So the dimensions, again, would be the length, the width, and the height of this box. Now we can move on to the second step, which is to state our primary equation. What are we trying to maximize or minimize? Well, in this case, we are trying to minimize the amount of material to be used. Anytime it's the amount of material, that's the surface area. So we are trying to minimize the surface area. So the surface area formula for a box is usually just the area of the two bases plus the area of all the sides. But this is an open top box, so it's just going to be the area of the one base plus the area of all the sides added together. So how would I write this in terms of these variables over here? Well, again, it has a square base, meaning the length and the width are the same measure. That's why they're both x's here. So the area of the base is just x times x, or x squared. Now the area of the sides, let's find the area of one side, and then we'll just multiply it by 4 because there's 4 sides. So what's the area of one side? That's x times h. So the area of all the sides would be 4 times x times h. So we have the surface area formula for our open top box. Next, we need to make sure that it only has one independent variable. Here we see that our surface area formula has an x and an h as independent variables. We can only have one because the goal here is to find the critical numbers. And to find critical numbers, we take the derivative of this, and we don't want to have two independent variables. So what we do then is we look to our given quantities to help us out. We are given that the volume of this open top box has to equal 1,000 cubic inches. So how can we use this? Well, the volume formula for a box like this would be length times width times height. And if we know the length and the width are the same, they're both x, we can plug that in here. So it would be x times the height, which is h, so it would be x squared times h. And the volume we know has to equal 1,000 cubic inches, so we can plug that in for that. Now what we can do is solve this for either x or h. It's probably easier if you solve it for h, right? Because you don't want to have to square root both sides. So let's just divide both sides by x squared, and we get that h equals 1,000 over x squared. Now what we can do, since h is equal to 1,000 over x squared, we can take this and plug it in to our surface area equation for h. Now all we have is one independent variable, x. Perfect. So let's simplify this. 4x times 1,000 over x squared simplifies to 4,000 over x. Now I have my primary equation with one independent variable. So I can move on to the next step, which is to find the critical numbers of this primary equation and then use those to help me find the maximum or minimum values. So let's go ahead and take the derivative of this primary equation. When I take the derivative of both sides over here, I'm going to rewrite this as 4,000 times x to the negative first power by bringing this back up. This will help me when it comes time to take the derivative because I'll just use the power rule. I don't have to use the quotient rule. So here, the derivative of x squared, I just use the power rule, becomes 2x to the first power. Over here, when I take the derivative, the 4,000 stays out front by the constant multiple rule. And then I take the derivative of x to the negative first using the power rule, becomes negative 1x to the negative second power. I can then simplify, and I end up getting that the derivative of my surface area equation, my primary equation with one independent variable, is equal to 2x minus 4,000 over x squared. Now, to find the critical numbers, I need to set this equal to 0 and solve for x. So how do I do that? I add 4,000 over x squared to both sides. I multiply both sides by x squared. I divide both sides by 2, and I cube root both sides. And I get x is equal to the cube root of 2,000. Now, you could leave it like this if you wanted to be exact, or if you wanted to round it to the nearest thousandth, we would say x is approximately equal to 12.599 inches. Now, before moving on, let's quickly determine, does this length make sense? Yes, it's not negative, it's not 0, so we can move on to our next step. Now, we found the length and the width in terms of our dimensions, but we need to figure out all the dimensions, so we also have to find the height. To find the height, remember, over here, when we wanted to rewrite the primary equation with one independent variable, we had the volume formula that we substituted in 1,000 for the volume, and we solved for h, and we got h was equal to 1,000 over x squared. That's why we plugged it in for h here. So over here, we can use that same formula, h is equal to 1,000 over x squared, and plug in the x value that we found. Remember to plug in the exact exact x value, not the rounded x value. So when we plug that in, we get that h has to approximately be equal to 6.300 inches. Now we can state our answer. Remember, we were asked a word problem, so we need to answer in a sentence. The dimensions that would minimize the amount of material to be used for this open top box that would still give you a volume of 1,000 cubic inches would be 12.599 inches by 12.599 inches by 6.300 inches. Now example 3 says the window below is constructed by adjoining a semicircle to the top of an ordinary rectangular window. Find the dimensions that would minimize the area of the given window if the perimeter is 16 feet. So we see that it wants us to find the dimensions that would maximize the area of this window. Because we're trying to maximize the area of the window, we know that this is an optimization problem, so we got to follow the steps. The first step is to make a sketch. Done. The second is to label any constant measures with a number, and any measures that we are trying to maximize or minimize, we need to label with a variable. So we are trying to find the dimensions that would maximize the area, so the dimensions are what we are going to label with our variables. That's why we have an x and a y to label the length and the width of this rectangle here. This x over 2 is just giving you the radius of this semicircle up here. Now that we have our variables and we made a sketch, we need to state any given quantities. What did they give us in this problem? They usually give you one thing. They say that the perimeter of this window is 16 feet. Next, what are we trying to find? What are our quantities to be determined? Well, we are trying to find the dimensions that would maximize the area. We just need to figure out what x and y are, so the length and width of this rectangle here. If we find the length of the rectangle, then we obviously can find the radius here, x over 2, so we don't need to write that. Now, in step 2, we need to come up with our primary equation. What is the equation that we are trying to maximize here? Well, it says we need to find the dimensions that would maximize the area of this window. So we need to maximize the area of this window. Well, how do you find the area of this figure? Well, it's a semicircle and a rectangle. So it's area of the rectangle, which would be length times width, and then area of a semicircle, which is area of a circle, pi r squared, times a half. Now we can plug in our variables that we're using here. The length and the width are x times y, respectively. And then the radius of the semicircle is just x over 2. So we plug those in, and then we simplify this a little bit more. X over 2 squared just becomes x squared over 4, which we can then multiply that to the 1/2 here, and we get something that looks like this. So now we have our area formula for this particular window. Because we have our primary equation, we can now move on to the next step, which is to rewrite it so it only has one independent variable. So here you can see we have an x and a y. We can't have both of those. Remember, pi is just a number, so we can leave that. But x and y, we can only have one because we need to take the derivative to find our critical numbers. So how do I substitute in something for x or y? Well, I'm going to go back and use my given quantity. What am I given? I'm given the perimeter of this window. So what is the perimeter of this window? Well, it's the length plus the width plus the circumference of half of a circle plus the width. So if I wanted to plug in these variables now, the length is just x, that goes in here. The width is y, that goes in here and here. And the circumference of a circle is 2 pi r. And the r in this case is our radius, which is x over 2. So we plug in for circumference 2 pi x over 2. Now we multiply that by half because it's only half of a circle. It's a semicircle. So now if I were to simplify that, I end up getting 16 is equal to x plus 2y plus pi x over 2. Now, what I'm going to do is I'm going to solve this for y. The reason is because there's multiple x's here, so that would be kind of tough to solve that. So again, I'm going to solve this for y. I'm going to subtract x on both sides and then subtract pi x over 2 to both sides. Then multiply both sides by a half, and I end up getting something that looks like this. So this is y in terms of x. Now, why did I do this? Because I can now take this, what y is equal to, and plug it in the area formula up here for y. When I do that, I have rewritten my primary equation to only have one independent variable, x. So now all I have to do is just simplify this. Here, if I distribute the x to each of these terms in here, and then over here, I can actually combine these, this negative pi x squared over 4 plus pi x squared over 8. If I were to multiply this by 2 over 2, and then add these together, I end up getting just negative pi x squared over 8. Now, I have my primary equation with only an x in it. So I can then move on to the next step, which is to find the critical numbers of my area formula. To find the critical numbers, I take the derivative of my area formula and set it equal to 0 and solve for x. So let's take the derivative here. Here, the derivative of 8x, the 8 hops out front. You just take the derivative of x, that's just 1. Here, the derivative of negative x squared over 2, the negative 1/2 just comes out front. You just take the derivative of x squared, so it'll be 2x to the first. Over here, this negative pi over 8 is going to come out front, so you just take the derivative of x squared, which would be 2x to the first. So now we have the derivative of our primary equation with one independent variable. So now to find the critical numbers, we just set that equal to 0 and solve for x. So what I'm going to do to solve this for x is I'm going to add x and pi x over 4 to both sides. The reason I do that is because I need to get anything with an x to one side so that I can factor it out and then get it all by itself by dividing both sides by 1 plus pi times 1/4, or pi over 4. Now, I don't want to have a fraction within a fraction, so I'm just going to multiply the numerator and denominator by 4, and I end up getting that x has to equal 32 over 4 plus pi feet. I'm going to leave it like this because I want to leave my answer as exact as possible. Now, before moving on, let's quickly determine whether this makes sense as a side length. Yeah, it's not 0, it's not negative, so we can move on. Now, I have found the length of this rectangle, but I need to find the dimensions. I need to find the width as well. What was the equation for the width? Remember, when we wanted our primary equation in terms of one independent variable, we solved the perimeter equation for y, and we found y was equal to 8 minus x over 2 plus pi x over 4. So we can then take that equation that y was equal to and plug in what we found x was equal to, and then we can simplify this. So how do we simplify this? Well, dividing by 2 is the same as multiplying this up here by 1/2, so it ends up looking like this. Same thing over here. Dividing by 4 is the same as multiplying this fraction up here by 1/4. Now, these have a common denominator, but this 8 does not, so I can multiply it by 4 plus pi over 4 plus pi so that it does. I can then distribute the 8 to each of these terms and then rewrite this so it's all under 4 plus pi. Combine like terms in the numerator, the 8 pi cancels out with the negative 8 pi. 32 minus 16 becomes 16. So the width of my rectangle is 16 over 4 plus pi feet. Now, since I was asked a word problem, I need to answer in the sentence. What were the dimensions that would maximize the area of this window? That would be a window with a length of 32 over 4 plus pi feet and a width of 16 over 4 plus pi feet. Now, example 4 says which points on the graph of y is equal to 4 minus x squared are closest to the point 0, 2. Now, this may not look like it at first, but this is an optimization problem. We're trying to figure out the shortest distance. We're trying to minimize the distance between 0, 2 and this function here, y is equal to 4 minus x squared. So we're going to go through our optimization problem steps. The first is to make a sketch. Done. The second is to label any of the constant measures with a number and any of the measures we're trying to optimize with a variable. So here you see they have already completed this sketch for us. We have this point 0, 2, which is not changing, and this point right here on the graph, as well as this point over here, will be our closest points to this particular point right here that lie on the function y is equal to 4 minus x squared. So we are trying to find x and y. So now we can continue step 1 of our optimization problem, which is to state the given quantities. What are we given here? Well, we are given the equation y is equal to 4 minus x squared. We're also given this point at 0, 2 that we are trying to get the closest to. Next, we want to state all quantities to be determined. So what are we trying to find? We're trying to find which points on the graph of y is equal to 4 minus x squared are closest to this point 0, 2. So we're trying to find x and y. We're trying to find that point, x, y, the closest point on this function to this point. So now we can move on to step 2 of our optimization problem, which is to state our primary equation. Remember, the primary equation is the equation that we are trying to minimize or maximize. In this case, we're trying to minimize the distance between these 2 points. So if we're trying to minimize the distance between 2 points, what equation could we use that would represent the distance between 2 points? How about the distance formula? And what we can do with the distance formula is plug in one of the points. We already know one of the points is 0, 2. So we could make the 0 x sub 1 and the 2 y sub 1, or we could make 0 x sub 2 and 2 y sub 2. It doesn't matter. I'm going to plug in 0 for x sub 1 and 2 for y sub 1. Now I have my primary equation. So I need to move on to the next step, which is to write my primary equation so it only has one independent variable. Here we have an x and a y. That's going to be really hard to take the derivative of, so we need to get rid of one of these independent variables, or write it in terms of the other. So how do we do that? Well, we look at our given quantities to help us out. We're given the point 0, 2. Okay, we already plugged that in. And we're given the curve y is equal to 4 minus x squared. Can't we use that to help us? Yeah, y is written as an equation in terms of x. So what I can do up here then is take 4 minus x squared and plug it in for y, because that's what y is equal to. Now all I have to do is simplify this, and I have my distance formula, my primary equation, with one independent variable. So let's go ahead and simplify this. I can drop these parentheses and do 4 minus 2 and just get 2. I can then square this here, and to square this, I'm going to have to FOIL it. So it's going to be 2 minus x squared times the quantity, 2 minus x squared. So when I FOIL that out and simplify, the x squared minus the 4x squared becomes negative 3x squared. The x to the fourth I bring to the front. Boom! I have my primary equation with one independent variable. Now what I need to do is take the derivative of my primary equation, set that equal to 0, and find my critical numbers. So in order to take the derivative of this, I'm just going to rewrite it. Instead of having a radical, I'm going to rewrite that as a 1/2 exponent. Now when I take the derivative here, this is going to require the chain rule. We have an outer function, this in here being raised to the 1/2 power, and we have an inner function, x to the fourth minus 3x squared plus 4. So when I use the chain rule here, I'm going to take the derivative of the outer function first. So it's going to be 1/2 x to the fourth minus 3x squared plus 4 to the negative 1/2 power. Then I'm going to multiply by the derivative of my inner function, the derivative of x to the fourth minus 3x squared plus 4. Now we can simplify this. This x to the fourth minus 3x squared plus 4 to the negative 1/2 power, I can bring down to the denominator so that it has a positive exponent. And the derivative over here, I just take the derivative of each term separately. Derivative of x to the fourth becomes 4x cubed by the power rule. Derivative of negative 3x squared, the negative 3 just stays out front. You take the derivative of x squared, becomes 2x to the first. Multiply the 2 and the negative 3, you get negative 6x to the first. And then plus the derivative of 4, that's just a constant, so the derivative of a constant is always going to be 0. Now I can multiply these together. This just comes to the numerator, and I have my derivative of my primary equation. But to find the critical numbers, I have to set my derivative equal to 0 and solve for x. Now here's the thing. With a rational function, the only way it's going to equal 0 is if the numerator equals 0. So we just have to set the numerator equal to 0 and solve for x. So let's do that. Here, I can solve this for x by factoring out a 2 and an x from each of these terms. I can then see that this times this equals 0. So I can use the zero product property and say that either this has to equal 0 or this has to equal 0. So I set each of those things equal to 0 and I solve for x. Over here, I divide both sides by 2. I get x is equal to 0. Over here, I add 3 to both sides, divide both sides by 2, and then square root both sides, and I get x is equal to plus or minus the square root of 3 over 2. Now before moving on, let's quickly determine if these make sense. Can they be 0 and can they be positive and negative? Yes, because we're dealing with a coordinate plane. We have x values that are positive and x values that are negative, and x is equal to 0 is an option as well. So each of these x values makes sense. We can use them when we move on. Now that I have my 3 critical numbers, I need to test each of them to see which gives us the closest distance to the point 0, 2. So I'm going to plug these x values into this distance formula that we found over here that only has an x in it. So we start with positive rad 3 over 2. If I plug that in for x in the distance formula over here, and I simplify, I end up getting approximately 1.323 units. I'm going to do the same thing for a negative rad 3 over 2. And then when I plug that in, I end up getting approximately 1.323 units again. Lastly, I'm going to plug in 0 for x in the distance formula over here, and I simplify, I end up getting 2 units. Now we look and determine which of these distances is the shortest. Well, that would be these two distances right here. They're the same. So we need to answer our question. It says which points on the graph of this function are closest to 0, 2. So to have points, you need an x and a y value. So let's just get the y values that go with each of these. So I'm going to plug in each of these to our original function up here for x and get the y value that goes with them. We'll start with rad 3 over 2. If I plug that in and simplify, I end up getting 5 over 2. If I plug in negative rad 3 over 2, I get the exact same thing. So our 2 points that are the closest to the point 0, 2 that lie on the function y is equal to 4 minus x squared are the points rad 3 over 2, 5 over 2, and negative rad 3 over 2, 5 over 2. And remember to answer in the form of a sentence because you were asked a word problem. Now, example 5 says a cylinder is inscribed in a sphere. If the sphere has a fixed radius of 10 inches, what dimensions would maximize the volume of the cylinder? So notice that it says what dimensions would maximize the volume of the cylinder, so we know this is going to be an optimization problem. So we go through our steps. The first step is to make a sketch, which they already give us. We're going to then label any constant measures with a number, and any measures that we're trying to maximize or minimize with a variable, and they already do that for us as well. So we then move on to the next part of step 1, which is to state any given quantities. What are we given? Well, the only thing we're given is that the sphere has a fixed radius of 10 inches. Then we look at what are the quantities to be determined. So what are we trying to find in this case? Well, it says if the sphere has a fixed radius of 10 inches, what dimensions would maximize the volume of the cylinder? So the dimensions of a cylinder, we're looking for the radius of the cylinder and the height of the cylinder. So that's what we need. We can then move on to step 2, which is to write our primary equation. So again, we are trying to maximize the volume of the cylinder that's inscribed in the sphere. So what is the volume of a cylinder formula? That's just pi r squared h. Sweet. So we have our primary equation. So we can move on to the next step, which is to get it to have one independent variable. So we need this primary equation that we have, our volume formula, to only have one independent variable. It can't have an r and an h. So what we're going to have to do is use something that we're given, one of our given quantities, and write a second equation that we can then solve for either r or h, and then we can plug something in here. So we look, what are we given? Oh, we're not even given like a surface area or anything. We're given the radius of the sphere is 10 inches, and the radius of the cylinder and half of the height of the cylinder, it looks like create a right triangle here. So we could then relate these three measures by using the Pythagorean theorem. We can go a squared plus b squared equals c squared. So it doesn't matter which one of these are a or b, it matters that 10 has to be your c. That's your hypotenuse. So what I'm going to do is use this as my a, this is my b, and this is my c. So I'm going to go h over 2 squared plus r squared is equal to 10 squared. Now I simplify h over 2, the quantity squared is just going to be h squared over 4. And now I have to decide, am I going to solve this for r or h, so that I can take that and plug it in up here? Well, it looks like it would be easier to solve for r. So what I'm going to do is subtract h squared over 4 on both sides, and I have r squared is equal to this. Now what I could do is square root both sides and get r is equal to the square root of 100 minus h squared over 4. Or I can look at my primary equation up here and see it already has an r squared in it. So I don't even have to square root both sides. I can just take 100 minus h squared over 4 and plug that in for r squared in the volume formula here. Now I have my primary equation with one independent variable. I can now move on to the next step, which is to take the derivative of my primary equation, set that equal to 0, and find my critical numbers. So if this is my primary equation, I want to simplify this first before I take the derivative of it. So I'm going to distribute the pi h to the 100 and to the h squared over 4. Now what I can do is take the derivative of this primary equation. To do that, I take the derivative of each term separately. The derivative of 100 pi times h, the 100 pi stays out front, and I just take the derivative of h, which is just 1. Over here, I take the derivative of negative pi h cubed over 4. The negative pi over 4 stays out front, and I just take the derivative of h cubed using the power rule, which is going to be 3h squared. I then multiply that 3 to the negative pi over 4 out front, and I get something that looks like this. Now what I can do is set this derivative equal to 0 and solve for my critical numbers. So to solve this, I'm going to add 3 pi h squared over 4 to both sides, multiply both sides by 4, divide both sides by 3 pi, and then square root both sides. And I get h is equal to positive or negative rad 400 over 3. Now that I've found my critical numbers, I need to think, does this make sense? Can you have a positive rad 400 over 3 and a negative rad 400 over 3 for your height? No, you can't have a negative height of a cylinder. So I'm just going to use the positive rad 400 over 3 inches as the height of my cylinder. Now, I have found the height of my cylinder, but I need to find the dimensions that would maximize the volume of the cylinder. So I need the radius as well. How do I find the radius? Well, if you recall, when we made our primary equation only have one independent variable, I solved for r squared. And we know r squared is equal to what we plugged in here for r squared, 100 minus h squared over 4. So I'm going to take this h that I found and plug that in for h in the r squared formula. I can then simplify this. The square and the square root cancel each other out. This then simplifies to 100 over 3, and when I subtract these two, I get 200 over 3. I can then square root both sides. Again, we're keeping the positive version. We We don't care about the negative version because you can't have a negative radius. So now we have both dimensions that would maximize the volume of this cylinder here. Again, this is a word problem, so you need to answer in a sentence. A cylinder inscribed in a sphere with a radius of 10 inches would have a maximum volume with a height of rad 400 over 3 inches and a radius of rad 200 over 3 inches.